Thank you all for joining. My name is Mayumi Hiramatsu. I run EC2 networking, and here with Dheerendra, who is one of our principal engineers, who's going to also talk about what it's like to be a principal engineer here. So looking forward to having a discussion. We're going to try to keep this short and then make it interactive towards the end. Can you guys go to the next page? All right, so here's a quick agenda. We're going to give you a quick overview of EC2 networking organization, just so you know what we're talking about in terms of our scope. And then some of the challenges that we work on, and especially the principal engineers, they're the smart ones in our organization that I'm always relying on, and then we'll follow up with Q&A. Let's keep going. So here's what we're doing from EC2 networking. And for those of you who are not familiar, AWS has two components of networking. There's the infrastructure of the actual cabling and the physical elements, and then there is the software-defined networking. Our group is software-defined networking side, so that's what we refer to when we talk about EC2 networking. And here's the problem that we're solving for the customers. Our customers initially were primarily cloud customers. They were maybe born in the cloud, and they love the cloud and they're experts. But as we evolved, what we find is that customers' world is really, really complex, right? They have data centers and job sites and branches and factories and all these locations already. Many of them, especially companies who've been around for 100 years, they have all these on-prem that they have to connect to. I'm hearing some background noise. If you don't mind potentially muting, that'd be great. Okay, so where we are with this is that on this journey, we went from having networking just for the cloud to now expanding it. And thanks for advancing the slides. So we think of it as AWS is in the middle, and then we have all these areas that we can get connected to and provide this cloud technology at the edge. And so these data centers, branches, or telco sites, actually, you might have seen some of our announcements around it. We're creating network services in those areas as well and connecting it and providing all these technologies that they didn't think they could ever have before. And it's really exciting because now networking is not just an underlying infrastructure, it's an enabler to actually do all this. And it's a really disruptive time. You can go to the next slide. And here's some key tenets. You might have heard of us really focusing on operational excellence, starting at the bottom. Security, availability, scalability, and performance are fundamental to what we do. We're always looking at what we need to do to improve that. And we're very proud of the fact that we're one of the most reliable, secure, and scalable cloud in terms of networking services. And there's a lot of innovation that goes into it because of our scale. Dheerendra will talk more about it. And then if you look at our user experience, we're really focused on what can we do to make it easier for these customers, because it is getting complex, as I showed you. So customers are always asking us that, hey, what can you do to make it easier to secure and scale? Security and scale is something that's really important to our customers who are growing really fast. And what do we need to do to enable their hybrid cloud network? They have all these locations. They want to easily be able to seamlessly connect. A lot of developers are saying, look, I don't want to deal with network complexity. I don't want to deal with IPs. How can you make it easier? How can I still have security groups and security constructs in the cloud without having to do all the work? So we're working on this developer and different customer experience, as well as centralized manageability and visibility. Next slide, please. And here's some examples. So if we look at some of these key areas that I just talked about, starting with operational excellence, we're the only cloud that actually has 3+ layers of security at the physical software layer, both virtual as well as like TLS. So when you think about what are some security areas we need to be doing, we're constantly doing it from the hardware all the way up. And we're always talking about reliability, not only the physical and software layer, like you would expect in the data centers, you might have redundancies, different feeds, different power supplies, but on the software layer too, we spend a lot of time making sure that we're always available and operationally focused that way. We're the only cloud provider with 400 gig instance of performance. And then, as I mentioned, we're the largest global scale, 24 regions, 77 availability zones, 220 POPs. And these availability zones, think of them as like different data centers, but connected by a MAN network on these 24 regions. Next slide, please. And I talked about, making it easier for customers. So here's some examples that we launched last year. We deployed AWS Gateway Load Balancer, which is a new load balancer that helps customers' virtual appliances to be load balanced. So that gives them scalability, availability, and of course, different types of things they might want to do, like A/B testing. We also have private link, which essentially is a way for us to connect different resources securely. We have 110 AWS services, 500 plus partners. Customers love this because they don't have to think about it. Is the connectivity secure? I talked about hybrid cloud, where we're focused on what we call Transit Gateway, which is essentially like we consider it as a cloud hub, connecting to SD-WAN that customers are already using, and manageability. For example, Transit Gateway has a IGMP multicast. Those of you might actually know what multicast is. It's commonly used in, say, financials and M&E, where you can actually send one packet and then distribute it out. So that's an example of what we're doing. And we have a laundry list, but I didn't want to go through all those. Let's go to the next slide. So in the end, here's how we think about AWS networking. It started off in the cloud. It was a cloud networking service. And now we're actually expanding to all these different locations. And you can imagine now we have all these really interesting challenges like, okay, great. We have these, software defined network at global scale. Now we have to shrink wrap it into small little footprints and put them all over these different locations because, we can't afford to have racks and racks of servers like we do in our own data center. So the challenge continues. And of course, like some of these are actually at a customer site. You might have heard of Outpost, which is actually our technology at the customer site. So now we're talking about remote management and being able to handle hardware and software capabilities at these different locations. So the challenge is always there at our scale and always trying to make it the right thing for our customers. With all this, we're also focused a lot on manageability and monitoring because it just gets so complex, and customers are now going to have to, they're going through logs at each of these locations trying to pull it together and see where their network issues might be. So we're trying to make it as easy as possible by providing a more cohesive single pane of glass type of monitoring, as well as depth where they can go into the details. Next slide, please. So why AWS EC2 networking? I talked about some of these, but let me just sum it up by saying we have scale like you won't believe. It's really, really hard when you have scale against you and the uptime that people experience. And we're a fundamental service, as you can imagine, to all AWS services. So really critical. The expansion to distributed cloud that I just talked about, we're always customer obsessed. So, sometimes we're doing some really, really hard things like how do we reduce the cost as much as we can so we can pass it back to the customer. These hard problems are hard. Like I talked about, we have millions of servers in a data center. How do we shrink wrap it into a small box and be able to put it at a telco site, and still provide reliability and performance? These are really hard problems that we all work on. And one of the things that I love is that we're constantly innovating on behalf of the customer, and it's super interesting to be here. Next slide, please. So with that, let me finish it up and give it to Dheerendra, who can actually tell you what kind of work that he does.
Sure. Thanks, Mayumi. Thanks for the background. Hi, guys. My name is Dheerendra Talur. Good afternoon to all of you. I'm a principal engineer in the EC2 networking Hyperplane team. We're going to do a deep dive on the Hyperplane platform today. A brief introduction about myself. I've been with the Hyperplane team since fall 2017. Before AWS, I spent 15 plus years building core internet IP routing infrastructure and some of the companies that you may all know about. And while I'm not doing this, occasionally you'll find me in one of the craft breweries around Seattle that dot the east side. I'm somewhat of a beer snob. And some fun facts about Amazon culture that I found really fun and interesting when I joined this company. At the beginning of every meeting, everybody quietly reads 1 to 6 page long documents, and those documents describe the problem, the proposed solution. Everybody quietly reads it, and then after everybody reads it, you start discussing it. It's a much more structured way of going about complex problem solving, and I really love that part. And when we do periodic team updates, with like monthly business reviews, etc., when we do customer deep dives on things that went wrong, we do it with the entire team. We do it with executives, with every engineering person in the group, even with the interns, right? So it's a very transparent environment. That way, all the engineers know what the executives are thinking about, and the executives know what the engineering team is thinking about. On a lighter side, Amazon has a very amusing tool called Old Farts that tells you how many people Amazon has hired after you. I just looked up myself last week, And I was astonished to realize 82% of Amazon worldwide was hired after me. So that's how fast Amazon is growing and hiring. Now, let's jump into a brief architectural overview of Hyperplane. What is Hyperplane? So Hyperplane is a platform on which many AWS services such as NLB, Network Load Balancer, NAT Gateway, Private Link, GWLB, which Mayumi just spoke about, and Transit Gateway are built. Many large and popular AWS services, internally, they also use Hyperplane. You may not know about it, but they internally use Hyperplane. What does Hyperplane do? It enables services, partners, and customers to focus on their core expertise. What I mean by that is, if you take the example of gateway load balancer, and then let's say you're building a firewall application. So the hard part about scaling the firewall appliances out when you need additional capacity and scaling them back in when you're done with using that additional capacity, consistent hashing so that flows in both directions, in both the forward and the reverse directions up into the same firewall appliance, health checks, monitoring, metrics, all of that is taken care of by the Hyperplane. You don't have to, as the application developer, you don't have to worry about it. The infrastructure provides you that capability. You can focus on your firewall appliance, which is your IP, and that's where your core expertise is. Now, here's a block diagram level overview of what the Hyperplane architecture looks like. Essentially, Hyperplane is a horizontally scalable multi-tenant distributed system. It's built on vanilla EC2 instances that all AWS customers use. We have if you decompose Hyperplane, we have 4 critical submodules. The first one is called, like the flow tracker. This is the central database that tracks all the flows that are known to the Hyperplane module. This is built on a horizontally scalable set of EC2 instances. We build them out in cells. So when we need additional capacity, we just stamp out these additional cells. And the flow trackers need other good capabilities, such as one-for-one redundancy. They need to be resilient to failures. And then we need to be able to upgrade software in a hitless manner. So all of this good stuff happens in that block. And then the next layer is the packet processor layer, which again is a horizontally scalable distributed multi-tenant system. What I mean by that is, when we need more capacity, when our customers need more capacity, we just add more packet processors dynamically, and then we remove them out once the customers are done using those packet processors. All the feature-specific logic of the packet processing goes into the packet processors. Most packets just bounce off of the packet processors. Again, these are built purely out of EC2 instances. A third block is our intelligent and distributed control plane. This control plane is responsible for distributing customer-specific information about what kind of features they want, what kind of services they have configured to the flow tracking layer and the packet processors. And when there is extra packet processors required, when there's more capacity needed, there is telemetry that tells the distributed control plane to scale these packet processors out. So that goes into the control plane. And also deprovisioning of hosts when the hosts fail or when additional hosts are required. All of that intelligence resides in the distributed control plane. Since we not only build our service, we also operate them. We have a very extensive test and service monitoring infrastructure around this Hyperplane platform. So what do the tests do? We have tests running in each of the availability zones that when we talked about 24/7. Those tests test for latency, they test for availability, they test for functional correctness. And whenever we see something's broken, something's not right, then we raise an alarm. And most of these errors, we're able to automatically correct them, but some of them require manual intervention. That's what test and service monitoring does. And also the telemetry we have in packet processors, we export a lot of that data through what we call as the Kinesis infrastructure to CloudWatch for the consumption of our customers. So our customers use that for billing and metering and those kind of purposes. So they have insights into what's going on into their services that they provision. Now let's deep dive into some of the scale related challenges with Hyperplane. Now, what kind of scale are we talking about? So we're tracking billions of flows. We are processing billions of packets every second. We are setting up or tearing down hundreds of millions of new connections every second. And then across all these 3 dimensions, we are growing exponentially. So this is the scale that we're talking about. So it is, quite challenging. Now let's double click into the flow tracking layer and try to understand what goes on over there, right? And what kind of scale, what the scale dimensions, what kind of challenges does it impose on the flow tracking layer? We looked at many of the off-the-shelf databases, but none of them have the scale, latency, and availability characteristics that we desire for flow tracking. Because we are a middleware box, middleware network box, like our applications, the applications that use our infrastructure, the Hyperplane infrastructure, they're very latency sensitive, and they're also very throughput sensitive. They want low latency and they want high throughput, right? So the flow tracking layer needs to be able to cater to those requirements. So what we do is we built our own distributed data store, and it has some of the nice properties that I talked about earlier, which is it is one-for-one redundant. Every flow that we know about is present in at least 2 places in the distributed data store infrastructure. And then the data store is resilient to failures. We expect that failures happen all the time. So hosts go down. The data store is resilient to failures. What I mean by that is the service does not degrade because of a single failure. And then we are also resilient to software deployments. We can continue to operate the service when we are deploying software to this distributed data store infrastructure. So those are some of the challenges with the flow tracking layer. Now, another challenge, an interesting challenge with Hyperplane is multi-tenancy. What is multi-tenancy? Multi-tenancy is the way we abstract shared physical platform out to customers so that every customer thinks that they have exclusive access to that shared platform. But in reality, the physical infrastructure is actually being shared, right? And multi-tenancy improves resource utilization because customers' spikes, their bandwidth needs are not, they go up and down. So we don't have to provision for the max bandwidth requirements of all of our customers. So whichever customer is spiking, they get more capacity. The ones that are not, they take less capacity. What it translates to is a very improved cost structure for the customers. But multi-tenancy comes with some interesting problems, one of which is resource arbitration with problems like noisy neighbor. What I mean by noisy neighbor is because we are sharing the physical infrastructure, it is possible that at some point in time, one customer spikes up their usage, meaning they're setting up more connections per second, they're pumping through a lot more traffic. Because the infrastructure is shared behind the scenes, there is going to be some impact of that customer on other customers who are sharing that infrastructure. That is what we mean by the noisy neighbor problem. And our goal when these noisy neighbor problems occur is to ensure fairness and predictable behavior, not just for our customers, but also for our platform. We want our platform to behave in a predictable manner when we run into congestion. And then what do? We detect, mitigate, and isolate noisy neighbors as soon as possible. That is our reaction mechanism to when these noisy neighbor problems occur. We use an interesting technique for some noisy neighbor related problems that occur because of multi-tenancy. And one of them is called shuffle sharding. So I talked about the horizontally distributed, the scale out architecture for the packet processors. What we see here are 4 customers, red, green, blue, and purple. They are sharing, they're sharded to these packet processors. What I mean by sharding is customer red has access, customer red is using 4 or 5 packet processors for their purpose. And similarly, customer purple is using n packet processors. But as you can see through the rectangles, some of those packet processors are actually shared between these customers. Now, it's possible that customer red spikes up their bandwidth, their resource usage. They start pumping in a lot more packets, or they start setting up a lot more connections per second because their application requires that at that point in time. What happens is the telemetry that we have in the packet processors, it detects the increased PPS or the connections per second, signals our intelligent control plane, and the control plane provisions additional capacity in terms of additional packet processor units for that red customer so that we can absorb that increase in load that the red customer wants at this point in time. And once that customer is done using that capacity, and once their PPS and the CPS goes down, we relinquish these packet processors automatically, and we make it available for other purposes. Now, you might be wondering where this term shuffle comes here, right? So there is a relation to like cards. So this is somewhat like, picking a deck of 4 or 5 cards from a pack of 52 cards. Instead of 52, like we have hundreds to thousands of packet processors in some of the availability zones. So we just place these customers on this packet process, very similar to picking cards from a deck, to reduce the probability of impact. But there are some interesting sub variables here, which is the shard size is different for each customer because their bandwidth needs are different. One customer may have like 5 packet processors, another may have 10, yet another may have 20. And then the bandwidth needs of these customers are continuously changing. They're not static. So the hotspots keep moving. So all of this rebalancing that all of this balancing that I was telling you about has to happen on a continuous basis so that our customers get a good experience. So the problem we're trying to solve is, given any 2 customers on the shared infrastructure, we want to reduce the impact of one on the other. Now let's double click into another interesting aspect of Hyperplane, availability. Now, what are our design goals for availability? In the presence of failures, we want the blast radius to be as small as possible. That's one of our design goals. We design a subsystem such that there is no single point of failure. We assume that failures are an integral part of the design process and the operations process, and we design for it, right? Failures are just norm. They're just part of life. And how do we detect failures? We continuously run tests, monitor for failures, and then we raise alarms when we detect failures. When the alarms are raised, many occasions, our automated systems can automatically mitigate the customer impact. There are some cases where we will have to manually jump in, and we do that. But overarching goal is always to mitigate the customer impact as soon as possible. Our development model is continuous integration and continuous deployment. We extensively test our code automatically as part of our deployment pipelines before we deploy code. And then after we deploy code, we monitor for failures. If our monitoring systems detect failures, we auto roll back. We go back to the previous best known version of the code that was working fine. That's what we do on detecting failures. Now, what does the future look like for Hyperplane, right? Now, I talked about the scale. So we want to continue to scale Hyperplane to meet the exponential growth that this platform is experiencing. We want to improve continuously our algorithms for noisy neighbor. We're not happy with where we are. We want to continue to improve how we deal with noisy neighbor problems. We want to improve the rate at which we want to detect faster noisy neighbor events faster. We want to mitigate them sooner, and we want to provide smoother scaling experience for our customers. We're always trying to reduce cost of the infrastructure for our customers. And we are enabling more loosely coupled architectures so that we can accelerate feature development. Development of one feature should be as loosely coupled with other features as possible. That's the goal there. Now, shifting directions a little bit, why EC2 networking, and what is it like being a PE in Amazon, right? Mayumi just talked about it a little bit. EC2 networking is a foundational service on which many AWS services rely. If you're building a database service and you have a bad day, it is that database service that has a bad day, right? But if EC2 networking has a bad day, because the blast radius is large, we end up impacting many other AWS services negatively. The blast radius of EC2 is large. So the reliability expectations of our software is high. Now, the other dimension is security. EC2 networking infrastructure must be secure. The software must be secure. Otherwise, we erode customer trust. When we say it must be secure, it is not just security for EC2 platforms like Hyperplane, EC2 networking platforms like Hyperplane, but for all the services that run on top of EC2 networking. So security is our highest priority. What we mean by that is if we ever had to trade off between a new feature and fixing a security thingy, then we always break towards security. And while designing our subsystems, we follow the principle of least privilege for security reasons. Now, another fun fact, what is it like being a PE in Amazon, right? Amazon PEs have some tenets and there's some expectations. The expectation from Amazon PEs is that we should have a resounding impact. No, it's not just enough to deliver results. What I mean by that is it's not enough to often scale service just 2x or 3x because the needs of the business are different. So we have to look for 1 or 2 orders of magnitude higher in terms of scaling service. And there are times when we'll have to come up with completely new services when none exists. That's what I mean by resounding impact. And then Ps are required to be exemplary practitioners. Principal engineers are embedded into teams. They drive technical direction of the teams. We're not just doing whiteboarding. We're not just doing some PowerPoint slides. So principal engineer contributions span architecture to design to code to operating the service, the entire gamut of the software development experience. And then Ps are also required to be technically fearless. The growth that we just saw for AWS leaves no room for conservative thinking. So Ps are expected to take risks. And then we also know that along with taking risks comes the a downside of occasional failures, and that is completely acceptable because failures are the stepping stones to success.